safer medical implants, better performing batteries, and more accurate industrial measurement tools. An international group of researchers and engineers have developed a new laser prototype that can texture miniature patterns on metal surfaces and thereby enhance their characteristics. It creates the so-called laser-induced periodic surface structures, or in short, LIPS.
Laser4Surf tried to push a little bit forward one of the techniques, that is that inducing surface nanostructures in the surface of metallic parts, and needs to put it, to move it from the lab to the industry, so to close the gap from research at the lab scale and put it into mass production, or at least a little bit closer to mass production.
The core of the prototype is an off-the-shelf femtosecond laser emitter. It produces not a continuous beam, but 500,000 pulses per second. The light pulses have a wavelength of 1030 nanometers, which means they are not visible to the eye. The beam is guided by an array of different mirrors through the setup. These infrared pulses are so powerful that they can drill, cut, structure and mill a metallic surface. During the scanning process, the laser pulses briefly transform the material to plasma. Once the plasma evaporates, it leaves behind a thin line structure. With this new beam shaping module developed by Multitel, it is now possible to adjust the shape of the light from circular to square, the polarization orientation and even the pulse duration of the laser. This enables the engineers to create up to 1,200 lines per millimeter on the surface material, or more than 120,000 lines with one single laser scan. During the lasering process, the travel stage moves back and forward, while the laser head moves from left to right. Each have a range of 1.2 meters, so they can handle also much larger samples. The microscope check reveals the LIPS pattern produced are accurate and have a periodic texture. The Laser4Surf project has worked with 3 potential end users who could benefit from such a technology. Rescoll, a producer of medical implants, is one of them. Medical implants are usually made of titanium. They are very durable and require high-precision production tools. But once such a device is implanted into our body, it needs to connect with human bones and tissues. A slick surface is counterproductive, so the implants need to be roughened, coated, or treated with a laser.
We have been working with coatings, but the drawback is you have to prove that your coating is going to really attach to the titanium, that during the positioning of the implant is going to remain there, and you are adding a new material. You have to prove the new material is safe and is functional. By laser, you are only modifying an existing material. So for the authorities, you have only to demonstrate functionality, but safety is almost done.
In a second case study, the research unit of CICe Energy Guna works on the improvement of electrical storage. They are interested in the effect of a treated surface of current collectors in lithium batteries. A rough surface connects better to the electrodes, so researchers studied which kind of laser-induced pattern would improve both the charging and discharging parameters of the batteries, and thereby also their lifetime.
We have to roughen this surface, so the contact is better and it sticks, so it doesn't peel off. This roughening, we do it in a non-controlled way right now. We just rub it randomly. The idea here is to, with the laser, do it in a reproducible manner and very controlled way. That actually is what the industry is looking for.
The third end user within the Laser4Surf project is Fagor Automation. They develop high-end optical encoders to measure the relative displacement in a machine. Such devices are used in high-precision manufacturing processes. The challenge was here to find the ideal dimensions of a LIPS pattern that would improve the functioning of an optical encoder. Again, the latest test results are promising.
In our final product, we are able to do this over tapes, stainless steel tapes, up to 60 meters, with an accuracy of, in tape, about 5 microns per meter. Not too bad.
All three end users are keen to adapt the new technology on their new product lines. Also because the laser machine comes with an integrated quality control unit inside this black box. After the laser treatment has taken place, the sample moves inside this unit for a thorough checkup using diffraction optics. When light is directed on the textures, the rays are diffracted depending on the induced surface structures. A software analyzes the pattern and verifies their parameters. Last but not least, a sophisticated software was developed by Ceit, a Spanish institute focused on applied research in order to convey the different units of the laser machine into one functional system.
As you can see, this is a full prototype, so it's fully open. Obviously, this is not very good looking, but the next step is to industrialize it and make it more robust, repeatable, reproducible as well. And also, for example, put an enclosure all around the machine, so that will make it safer and more user-friendly to use, like a real production machine.
How such a machine will look like can be observed in one of Lasea's test facilities. Here a robot is linked with the laser machine to fulfill certain tasks. The texturing with the laser is done inside the enclosure to avoid contact with the workforce. The other assembly activities are taking place outside the laser machine. After 42 months, the project Laser4Surf has come to an end. The consortium has created an all-in-one laser texturing machine that will now take a further final step before reaching the market. Lasea, the manufacturer of the machine, expects to deliver the first units within the next 12 to 18 months.
Of course, all these things must be integrated in one machine to produce a prototype, lab prototype that will have the beam shaping module, that will have the inline monitoring system, and of course, they will have the tool to predict the LIPS period for different materials. And of course, this is the introduction of what the project was all about. I think it's time for me to stop this presentation. Yeah, there we are. I don't know if there's some questions about this, but it's probably not, because it's only the introduction. But now I will pass the torch. I will pass to Yves Hernandez from Multitel that will explain us everything about beam shaping and polarization in the framework of Laser4Surf. Yves, whenever you're ready.
Yeah, so I hope you can hear me. So thanks a lot for participating to this event. I am Yves Hernandez from the Research Institute Multitel in Belgium. I will present here the work done by my colleagues Alexander Jacek, Hendrik van Opsten, and Julien Dupuy. And they worked on the beam shaping and polarization control. As Yago just explained, it's an important part for getting regular homogeneous lips on different materials. Just a few words about our institute before, if you permit, before I start the description of our work in the project. So we are a research institute based in Belgium, about 60 kilometers from Brussels. We are mainly an ICT institute with 4 different departments: applied photonics, signal and image processing with artificial intelligence, human-machine interface, developing embedded electronics, and my colleagues from wireless communication are mainly working on cybersecurity and cryptography. In the applied photonics department, we develop fiber laser sources from CW to femtosecond in the mainly fiber laser, so it's mainly with ytterbium, thulium, and erbium fibers. We do material processing optimization in different research projects. We also work with CW to femtosecond, so we can either work on joining as well as surface texturation. We have also an activity related to biophotonic sensors. We develop mainly the interrogation system, so how to collect the light from lab-on chips, for instance. Here you can see a picture of a multi-channel spectrometer that we developed in a previous project. We do terahertz imaging and spectroscopy as well, so we have different commercial devices in our labs for making this spectrum and these images, and we also develop our own solutions in the lab. And finally, we do fiber optical sensing with developing mainly the interrogation systems for different applications. We have a lot of projects with aeronautics on this topic. So that's all for Multitel. I will just now jump to the work in Laser4Surf. In Laser4Surf, our role was to develop the optical modules. So Yago just presented them. It's the optical modules mainly to control the polarization orientation of the light and the beam profile in order to get something very homogeneous on the sample. And these modules should be compatible with the 3 different applications: the medical components, the advanced batteries, and the linear encoders. And as said before, it's for industrial applications. So an important thing is that these modules can be integrated in the laser machine, can be interfaced, synchronized, and so integrated mechanically, optically, and also from the software point of view inside of a real system. So this is a picture of the machine you just saw before. Basically, this system is a type of system built by Lasea. It's based on the ultra-short laser source, a scanner that will permit to focus the beam and scan over the sample. You have the system for quality control that is developed by Iris in this project. And in between the laser and the scanner, there is a beam shaping module that is needed to convert the Gaussian beam into a top hat beam, mainly to get something really homogeneous on the sample, and also to orientate the polarization. And as I said before, it has to be connected with all the elements of the machine. So you have to be able to synchronize, for instance, the rotation of the polarization with the scanner if you want to make different orientations in function of the path of the beam. As well for the beam shaping, if you use a dynamic beam shaping, you would like to have the possibility to correct the beam, for instance, in function of the results you get from the quality analysis. So our aim again is to develop these modules that could be integrated in the full system. The linear polarization orientation control is useful in order to decide the way you want the lips to appear along your beam traveling on the sample. So we have a linear polarization from our ultra-short pulse laser, and we want to orient it ideally in a synchronous way with the movements of the beam. So it has to be synchronized with the scanner mainly. You can see from this example from literature the impact of the orientation of the polarization on the patterns realized by lips. So we need something that is quite easy to use, that can work in real time, so it can be very fast, and that can be interfaced with the scanner. We use quite an obvious solution, which is to use a motorized polarizer on a wave plate. So this system was implemented rapidly at the beginning of the project and interfaced with Lasea system. it permitted to control the orientation of the polarization rapidly, well, almost in real time. And the second part that was more, let's say, that needed more efforts in development was the laser beam shaping. We need to go from basically Gaussian to a top hat. This is for almost all the applications in the project. We want to get something regular, but this aspect was particularly interesting and important for the encoders. We have two main options for getting top hat beam, is to use diffractive optical elements or spatial light modulators. And actually in the project we tested both options. Why? So the reason is that each solution has its own advantages and drawbacks. If you use a DOE, it's a passive component. It's quite compact. It's easy to handle. It's easy to integrate. It can sustain very high power. But the drawback is that it has a fixed shape. You cannot easily change the shape, or at least not that dynamically during the process, which permits to do an SLM. With the SLM, you have an active component, and then you can more easily or more flexibly change the beam shape of the shape of the beam during the process. But one problem with the SLM is the power handling. That can, for some applications, be a limitation. So we integrated both options together with a polarization controller. The first module we did included the DOE and the polarization rotation system. It's very compact. It was integrated directly at the input of the scanner. And the second module, based on the SLM, also with its own polarization control, was also included in the machine. And actually both systems was integrated on Lasea system. I will show you at the end. The first module is a DOE, so you have an input beam, which is a Gaussian, and with a very compact design, we integrated all the polarization control and the DOE in front of the scanner with a 4-screw auto-align, let's say, fixation. It makes the thing easy on the way that if you want to change the DOE, you can easily change the full module without realignment of the beam. So that's the interesting point for this system that, as I said before, is not as flexible as the SLM. So you can see an example of the shape that we got at the output of this module. The second system with the SLM, as I said, there's some limitations in terms of beam handling and power handling. You see on the curve on the left, on the bottom left, that we made some tests at the beginning with a nanosecond laser, and we observed a rapid heating of the surface of the SLM. In order to avoid this problem, we developed just a small system for regulation of the temperature of the SLM and to control the temperature. As you can see in the curve in red, that this temperature was kept very constant in function of the beam of the power injected on the SLM. You have a picture of the SLM on the top, and with this construction, we were able to use the SLM up to 100 watts in CW mode. In nanosecond, we can reach 1 millijoule per pulse, and as well in femtosecond, 1 millijoule and 2 gigawatt power. So we had, let's say, more than enough power handling with this system for the applications targeted in the project. This is a design of the SLM module. You see it's larger than the one with the DOE. Inside of the box, you have 2 flip mirrors at the entry that permit to bypass the SLM, and then you can leave the SLM fixed on the laser micro machining system, and then you can easily switch from the use of the SLM to the use of the DOE that will be placed afterwards on the beam line. So the first mirror will just reflect the light to the SLM, with afterwards a second mirror and a polarization controller at the end, just before going back to the original beam direction to the scanner. This is implementation. You can see here the SLM module and the DOE. So the light will come through the two holes, just as we showed before, is reflected by mirror here, go on the top, enters into the DOE, and then will go to the scanner. The system includes all the control and is interfaced with all the software and the control unit of the machine. And then it's easy to remove the DOE, use only the SLM, or put the DOE, switch the flipping mirrors in order to leave the light going through the module without being affected by the SLM, and then use the DOE. So you can easily switch from one component to the other. Just some comparisons that we did here in the lab with the DOE and SLM. We made some tests on silicon first, just to check the homogeneity of the patterns, so without beam shaping and with beam shaping in the two cases. And we also tried to make some LIPS experiments on stainless steel. Here you can see on the first two images the polarization control. So here you turn the polarization in function of the direction of the beam, and you can see here that we have lips that are transverse to the beam, and here lips effects that are longitudinal to the beam. Regarding beam shaping, you can see here the lips obtained with the Gaussian beam, and here the lips obtained with the flat top generated by the DOE, which is much more regular than what we can get with the Gaussian. In this case, we have about 800 nanometers periodicity and a depth of about 150 nanometers. So we developed the two modules, polarization and beam shaping, based on DOE and on the SLM solutions. Both systems permit to get flat top shape. With the SLM, it's even possible to do other beam shapes. Both systems are installed at Lasea on Lasea machine. There will be a presentation later on by Lasea explaining all the results obtained with these modules. With the DOE, we can have precise lips patterns with 1,200 lines per millimeter, with a focus post of 10 micron, which is very important for the encoder application. And the comparison between DOE and SLM can be done on a single system, which is very important with the system at Lasea now. Thanks for your attention.
Thank you, Yves. I think you have one question from Massimo Bonfante. So he's asking you, the laser beam output from the DOI is expanded and collimated? That's a question. Or you need to put a beam expander between the DOI and scanner. Which is the aperture of the scanner?
I will ask the help of Julien if he's connected, but we use a beam expander. I think it's after the DOE. Regarding the aperture of the scanner, I do not have the numbers in mind. So Julien, if you are connected, maybe you can answer to the questions. I don't think if Julien, which is attended, can get access to.
Yes, do you hear me?
You can. Okay, yeah, it's working.
Yes, I'm Julien Dupuy from Multitel, so I work on this module. So for the DOE module, we design and we purchase DOE directly, which work with a good collimated beam of the laser machine. So we directly put the module at in front of the scanner, so we don't need a focus lens or a beam expander. It's directly designed for the beam generator, which work with the laser machine.
And the aperture of the scanner, I think that was the other question.
And the aperture of the scanner, in fact, is around under 15 millimeters, I think.
All right. Happy, Massimo, with this? I think the answers has been effectively answered, the question. So thank you. Let's move on. We are still on time, which is always a feat. So for the second technical talk, it's going to be my colleague Aldara from Ceit, who will be talking about the parameter selection tool. That was the second challenge we described in the introduction. Aldara, whenever you're ready.
So good morning to everybody. Thank you for the presentation. This presentation is entitled LIPS Parameter Selection Tool. It will be a description of the software platform that will enable industrial end users to select the process parameters that give rise to a desired functionality without a need to deeply understand the LIPS generation process. So the application will ask to the user for a desired functionality and a specific material. The application of the software tool is going to search in the database for a set of process parameters in order to get a successful process. And the required process parameters are presented to our storage and send it in a file to the prototype equipment. So in this slide, we were gonna present the general structure of the software tool. You can see, well, it's divided in two parts. In the left side of the screen, you can see the part A, which is related with the generation of the LIPS as a function of the process parameters. In the right side, you can see the B part, where it's related with the generation of large areas of functionality. With large areas of texture surfaces with a particular functionality. As I said, this application of this software tool follows a database structure. So we're gonna make a walk along the different tabs. In the first one, the materials tab, you can visualize all the materials. Also, you can add a new material and also modify them. For the second tab, the samples tab, also you have a list of the available samples, you can add a new one or modify the existing ones. Before we are generating the process parameters, we can modify the properties of the actual status of the laser. This involves the power with the calibration measures and the relations between the beam expander and the beam waist. These are this is a machine dependent parameters, so it's not modified, are not modified in the daily base. Should be changed only when a calibration or alignment of the system is performed or are performed. In the A process tab, we can add all the process parameters to generate the different LIPS units, as you can see here. As we know, the LIPS units are more, strongly influenced by the scan speed and the power, but also many other parameters of the laser parameters can have an important influence in the LIPS generations, as the wavelength, beam waste, repetition rate, polarization. So many combinations of laser parameters can be done. So one of the benefits of this software tool is that the end user, the application is going to show to the end user only the appropriate combinations or the appropriate conditions to generate LIPS units. In the LIPS units tab, we can search and visualize all the generated LIPS. And also you can modify and introduce the results of the process. Some of these characteristics should be the period, the line width, or also the electronic microscope image. And now in the process results, I'm gonna play a video in order to show how to manage or to analyze the results. So in this tab, we can see the results, but although all the results can be seen, you can use the table filter in order to filter the results by the specific material and a defining range of parameters, as you can see in the video. So the results are shown in the screen with the characteristics of the LIPS units and the process parameters. Some of these results can be selected and export to a CSV file, which is going to be transmitted to the prototype machine since they have the conditions to generate the LIPS. Also, we can create a graph in order to analyze the results with the data in the x-axis, y-axis, and the series. And also this graph can be exported. In the B process tab, as I said before, now we can analyze, we can introduce the combinations, the geometrical combinations of the different LIPS units. So here we can add 4 different LIPS units in the same sample with certain separation and orientation. So as I said before, many combinations can be possible, but for the end user, it's going to be show only the appropriate combinations for a certain functionality. In the combinations tab, we can search and visualize these combinations, the results obtained, and insert the results of the process depending on the application. For example, you can see here some characteristic of general aspect, like the LIPS orientation angle. If the sample is an implant, we can introduce characteristic parameters as the cell affinity. If we have linear encoders, we can introduce the electric signal, for example. In the case of batteries, the capacity rotation, for example. Here again, we have a video where the B process results are shown. In this tab, again, the combinations, the geometrical combinations can be filtered now with the specific material, but also by the application. So in this case, we are searching for linear encoders with a particular defined range of electrical signal, and also these samples can be ordered by the electrical signal. Again, if we want to have some results of copper in the application of the batteries, so we can search for certain range of capacity rotation, and the samples are shown, and also we can order it again by increasing. And these results can be selected and exported to a CSV file in order to be transmitted to the prototype tool. So finally, I would like to make a summary of conclusions of the benefits of this database or the software tool. It shows the process parameters required to obtain the desired functionality for a specific material. Everything without to know many things about the process of the generation of the LIPS units. Enable the end user to select a specific functionality from a previously defined database, and allows the transfer the optimal laser parameters to the LIPS equipment to configure for the desired pattern. Finally, these are the partners that were contributing to generate the data that are in the database. Thank you very much. I don't know if there is a question here. Or...
It doesn't seem that we have. Okay. Maybe we have a question. Let's see. Please share your questions in the Q&A section.
Dr. Tim Kunze, apparently you had a question.
Thank you, Aldara. Moving on for the next. Talk. It would be Laurent Philippet from Iris Technology, explaining the LIPS monitoring system. There will be another talk. So this is the third of a series of 4 talks. We'll have a coffee break at 11:30. So just hold on a bit if you are in an urge for a coffee, because I think it's well to have these 2 talks. Laurent, whenever you're ready, thank you.
Thank you, Santiago. Let me know if you see correctly my screen. I think it should be the good. I have good screen you are showing right now.
Laurent is seeing the preview screen.
It's not the good one.
It's the other one.
Again. This one?
Yes.
Okay, perfect. Thank you, Santiago, for the introduction. It's a pleasure for me to have the opportunity to present the work done on the LIPS monitoring by Iris. So my name is Laurent Philippet. I'm Senior Optical Engineer at Iris. And I would like also to introduce my colleague, Dr. Aldo Ramirez Reyes, who is the project manager at Iris for this project. So I will. So this is this will be the outline of my presentation. So I will make a very short introduction of the Iris company, our role in the Laser4Surf project, the main output and result for our work, and I will finish with some conclusion and perspective. So IRIS is an advanced engineering company. We are based in Barcelona, in Spain, and we focus on key enabling technologies for digital transformation, for making industry smarter, more sustainable, and efficient in the industry 4.0. So we are specialized in different process monitoring, control, and optimization of industrial solution, mainly based on NIR spectroscopy. So here you have an example of 3 main products we develop at IRIS. We have a portable NIR analyzer that we call the Visum Palm, based on NIR spectroscopy. We have also another solution for conveyor application based on hyperspectral imaging. And we have also a solution for a pipe application where we have inline integrated NIR analyzer. So what has been the role of IRIS in this project? So as Santiago said in the introduction, we were in charge of the design and development of an inline monitoring unit for the continuous quality control of functionalized metallic surfaces. So we are providing a rapid, immediate, and reliable result for the main LIPS parameters. Santiago said that one technique is to go directly to the lab microscope, so which is quite time consuming. It's offline measurement. So here we offer instant and accurate and immediate result. And I would say that the monitoring unit, I would say this may be the last and critical element of all the inline laser texturing prototype, mainly because it's the last element that give the final result of the texturization made by the laser. So I would like to briefly introduce the diffractometry principle for the attendants that are not familiar with optics and photonics. So basically, it's a very common phenomenon in optics and photonics that occurs when light waves pass through a small aperture or illuminate a surface with very small periodic structure. So it's also an interference phenomena. And by the analysis of the diffraction pattern, you can retrieve the property of the surface. So a very known example is the left picture, when you have a laser diode that illuminates a very small circular aperture, and you can see that you have a bright spot after the circular aperture, but also interestingly you have successive rings of bright intensity and dark intensity, and this is typical of interference and diffraction. And another example on the right is when you work with gratings. So gratings have also periodic grooves. And when you illuminate this grating with a white light, so you have what we call different order of diffraction. So you have the order 0, where the light has not been diffracted, so it's reflected in the same angle of the incident angle. But the interesting point is on the left, where you have all this rainbow effect, where you see all the different color of the white light in one order of diffraction. So sometimes there is more than one order of diffraction, but this is a typical example of the diffraction phenomena. So what we done at IRIS, so we developed hardware based on image analysis of the diffracted light, and we also developed the software with the user-friendly interface that give the main parameter of the lip structure that we analyze. So basically, this is the main results that the image analysis software is able to provide. So typically 3 type of results depending on the quality of the LIPS parameter. So when the software detects that the parameter measure are the one that was expected, then it gives back this green light. Okay, this is a good sample with LIPS. This can also be a sample with LIPS, but the parameter measured by the software are not in the expected range. So this is also okay, but not as good as the first example. And so sometimes it can happen that the analysis is not possible for a different reason. Image can be saturated, but the user can change. They can decrease the exposure time, but also the LIPS are not detected, or there is no LIPS on the surface. So then this result is no. The sample has not been texturized with the good good parameter. And this is also my next slide. That so in addition to the measurement of the standard LIPS parameter, let's say, we were also interested to develop image-based algorithm for the detection of surface defect that can compromise the functionality of the LIPS. So here on the left, you have a picture, microscope picture of the LIPS when the process has been done correctly. And on the center, it's an image where probably the laser power was too high, or the scanning of the laser was too slow, and then no LIPS has been texturized, but instead some ablation effect. So this we can detect, and also other condition that maybe the scanning was too fast, or other type of condition of the laser, and then we detect the presence of some nano bubbles on top of the LIPS surface. So this is also something we can detect with the software. So I will so now I'm now with the conclusion and the perspective. So in this 3 years project, we have been able to design and to build a monitoring unit prototype, able to differentiate between different LIPS surface patterns for a large, let's say, large range of periods, from hundreds of nanometer to few micron. What is also interesting is that we can make some adaptation or modification, and we can change this range of detection according to the final application. And we have also been able to measure different type of sample, different form for different application. So aluminum foils, you have a picture when you see all this color characteristic of diffraction. We have been also able to detect LIPS on titanium cervical plate. Here also you can see this nice color effect. And the stainless steel encoder. Maybe it's less obvious to see the diffraction, but believe me, the LIPS are there. And we can also detect on 2D sample and also a 3D sample. So the titanium cervical plate, it's a 3D object. And yes, and the main application of this project were for advanced battery, medical components, and linear encoder. And I mean, we believe, and also the other participants in this project, we believe that there is a high potential for covering other application that we didn't study in this project, and that request also a fast and accurate inline quality monitoring control with a low-cost massive production of functional surfaces. So Santiago already mentioned some application of self-cleaning surface, like the touchscreen, anti-weighting surfaces There is also increase the light coupling for LED out for the output of LED of the efficiency of solar cell devices. But I think later in this workshop we will cover more interesting application. Talk will be given by Ceit at 12:30 for the new opportunities for LIPS technology. So I won't insist too much of the future application. And yeah, I would like to say that if any of the attendees has needs for monitoring analysis in the use case presented today, and would like to know more about our capacity, just I would like to say, please get in touch with us. I let here my email, Laurent, Philippet, and my colleague Aldo Ramirez Reyes. So we will be happy to receive your query, your email, and happy to reply also. So thank you very much. It has been a pleasure for me.
Thank you, Laurent. Maybe there are some questions about the LIPS monitoring for Laurent now.
Yes.
Let's see. No, nothing's coming. So thank you, Laurent.
You're welcome.
With the last talk before the break, it's going to be David Bruneel discussing and describing the full Laser4Surf prototype, the integration of all these modules. David, whenever you're ready.
Good morning, everyone. So I hope you see my screen well. So I'm going to present this is the last technical presentation for this morning, for this session. I'm going to present the full Laser4Surf prototype, which combines all the different modules that has been presented just before. First of all, I'm going to present first the Lasea group, who we are. So we are several subsidiaries with the headquarters based in Liège. We have recently acquired the company Optical, which is now a part of the Lasea group. And we also have subsidiaries in Bordeaux dedicated to optical systems. So these are now different locations. We also have different application laboratories and subsidiaries in USA, and also some distributors all around the world. And very recently, we have moved into a new building. So as you can see here, we have 3 floors and a capacity to produce up to 16 automated machines and 50 laser systems simultaneously. And we are strong of very good experience, a very large production area, more than 1,500 machines around the world, more than 40 patents. We are spread over 5 continents and plus 20 years of experience, and this all over 5 sites. So we are a laser solution provider, and here are some pictures of our facilities and laboratories of manufacturing of our machines. So now I'm moving towards the motivation of our participation in this project. So the different sectors that were targeted, we targeted 3 different sectors and applications. First of all, the energy sectors for batteries, to improve batteries, and then the medical and pharmaceutics sector, and metrology for improving linear encoders. So why we wanted to target those applications? So batteries, medical implants, and linear encoders is because of their currently the state of the art of manufacturing those components have some drawbacks. For example, they can be quite invasive, complex. You can need some very strong cleaning, like for example, sandblasting when you are texturing medical implants. And you can also have some complexity also, as well as toxicity in some cases, like for example, in the manufacturing of linear encoders, which are currently done with photoresist assisted lithography. And so the idea is to replace several steps of manufacturing of those different processes by a laser machine. So the objective of the process was to provide an automated workstation. So this is an overview of the sequence of actions. First of all, communicating with the different modules, the database from Ceit that was presented earlier, send the Multitel from the module from Multitel in order to automatically control polarization and laser parameters. And also to finish, we also, once the texturation is done, we can analyze the result thanks to the monitoring system developed by Iris. And all this was controlled and integrated into the machine, into the prototype. As you can see some picture here with the different components. So that includes the LIPS parameters tool from Ceit, the polarization and beam shaping module from Multitel, and also the analysis module from Iris. So now I'm going to present the validation and the results obtained. So first of all, when loading the parameters from the database provided by Ceit, so we have to reproduce the result on the prototypes, the result obtained by Ceit on the prototype. And so for that, we had to develop a conversion tool of parameters, which loads the database from the parameters from the database, and then we convert it through some calculations and some conversion functions in order to have the right parameters or the adapted parameters adapted to the prototype. And this can be applied to any prototype. So this conversion takes into account the very specific technical aspects in order to have the right results and the same results on the workplace. And so here are some examples of results. So here, for example, for the batteries application, we could texture a large area of more than 200 millimeters by 300 millimeters. And this was done on copper and aluminum. And we could prove the reproducibility of the parameters coming from the database on the workstation. We had the exact same results in terms of LIPS characteristics. So here are some overview of the samples. So on the left, it's for the copper foil, A4 format copper foil, and on the right, aluminum foil. Some other examples of results of implants this time. So here we are talking about 3D shapes. And so we had to reproduce the parameters and the pattern of the lips, the exact pattern on the lips, not only on 2D, but also on 3D shapes, as you can see here. So the goal was to texture the thread of the screw, as you can see on the right picture, so the gray band. We have done this as well on cervical implant, which is also a 3D part. To do that, we have worked on what we call the 7-axis technologies. So we have done some development on 3D trajectories that combines actually trajectories of 5 mechanical axes, so X, Y, Z, and 2 rotary axes. And those are combined with 2 optical axes coming from a scanner head. So from a 3D file, we can load it into a CAD/CAM and define the trajectories, thanks to our tool developed here, in order to have 7-axis trajectories, which are taken into account, so the specifications of the texturing with a scanner and the shape of the sample. So here are some examples of results. So here we have on the right a zoom of the lips obtained on the screw. And here this is a short video of how it looks like into the real life. So this is accelerated. And here are some other results of encoders. So we were able to prove the reproducibility as well of the lips. And this time on surfaces of 100 by 5 millimeters square millimeter. So we could have very nice lips, quite well aligned all together. So this texturation was to make a two periods pattern with, so we have the pattern of the lines and also the pattern of the lips at the same time. So we could to conclude, we could prove the validation of the full prototype from the conversion of the parameters that was proven. And so the appliance of these parameters onto the workpiece thanks to through hardware configuration, thanks to the Multitel module to control polarization and the laser parameters. Then the processing itself with those components, and then at the end, the validation of the part thanks to the monitoring system developed by Iris. So thank you for your attention. Here are some nice pictures of the results obtained. And to conclude, I'm going to move on the video made at Lasea to see the full prototype.
Here, this is a prototype resulting from the Laser4Surf machine, which has been developed by Lasea, in which we integrate different components, such as, for example, this laser, which is a femtosecond laser, 20 watts average power, so emitting a wavelength 1030 nanometers and 300 femtosecond. And here we have another component resulting from the Laser4Surf project, which is the optical module of this project, composed of different optics, special optics, and with a control of polarization, for example, and also control of the beam shaping with SLM that we can control thanks to our software CICe. Here, this is a zoom inside the Multitel optical module. So we can see the SLM, which is over here, for example, and we can see that we have the different optics in order to image the phase of the beam at the right position on the optical path of the machine. As you can see, the optical path of the machine is quite long, and so this has to be taken into account for the application targeted inside the project. So behind all this, there is a lot of calculations, as you can imagine. So as you can see here, so this Laser4Surf prototype has been designed to machine and texture very large areas with lasers. As for example, we have integrated a very long travel stage of 1.2 meters long, and we have the same stage on the other side of this gantry with the same travel length. As you can see as well, we also have some different modules and optics, and mainly so we can see here what we have LS shape, which is a module specially designed to control the power of the beam and also the polarization of the beam as well. So and now I'm going to the front of the machine to show you some other components. So as I said, here we can see that we have the other axis, a long travel axis of 1.2 meters long, on which we can see that we have a LS scan, which is a galvo scanner that will move the beam at very high speed on the workpiece. By very high speed, we mean several hundreds of millimeters per second up to few meters per second on the workpiece. And here we have another result of the Laser4Surf project, which is the online monitoring developed by Iris. And so we have a full chain of texturing and analysis, everything in the same global machine. So as you can see here, we have an overview of the global system, the global prototype developed in the Laser4Surf project. As I said, there are different modules integrated into this prototype and controlled in our software CICe. Below these modules, there is also modules developed by Ceit, which is a research center in Spain, which is integrated in our software CICe. And as I said, so this is a prototype, so this is why it's fully open, and you can see all inside actually. And but this is a prototype based on LS6 standard and series machines from Lasea. And so in the future, we can imagine that there will be an enclosure that will be all around the machine in order to make it safer and to be industrialized.
So thank you for your attention.
Thank you, David. It's time for any questions related to integration on these hardware modules. If there's any question, we can answer them now. Anyway, this is the last talk from the first part. We've been mostly and surprisingly on time, actually. That's very good. Thank you for the guys who did the talks, that we actually were very, 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 very good to delivering on time all the information. Let me say that we have a second set of talks after the break. We'll discuss in depth basically the three applications, the applications to medical implants, the applications to optical encoders, and the applications on batteries. We'll have a fourth talk about other opportunities that we have discovered while performing all the tasks of Laser4Surf. So now we'll have a 20 minutes break. We'll be back at 10 to 12, just to have a bit of rest for the body and the mind. But please don't miss out the rest of this web conference. Will be focused on the applications. I hope to see you later. Okay, 10 to 12. Any kind of thing to add from Elma, from anyone from the consortium? Anything you would like to add? No? Yeah, 10 to 12 it is. Thank you. So just for you, the people who has joined us, just introducing the second part of the digital conference, which is focused on success stories, focused on applications. So we have 4 main talks. I have to say that the first part was brilliant in the sense that it was a long time. Very well done by the speakers. Let's hope these second part speakers stick to the time, because otherwise 3 hours it's a bit long, so we have to be very careful with it. All right. And the first application would be about medical implants. The second application would be optical encoders, and the third one, as stated here, would be about batteries. Okay. Then we have Mikel talking about other opportunities, other applications that we discovered, or we just kind of realized when we execute the Laser4Surf project. And then there will be a very brief closing remarks, like an executive summary of the achievements of the project. All right. My name is Yago Olaizola. I am the acting chair of this digital conference. I work for Ceit, which has been the coordinator of this Laser4Surf project. Okay, so the first speaker is going to be Marilys Blanchy from Rescoll. It's going to discuss the application of lips in medical implants. Marilys, whenever you're ready, you take charge of the presentation.
Perfect. Thank you very much, Yago, for the introduction. I will try to be as good as the previous speaker and not to be over the time. So just don't hesitate to interrupt if I'm too long to talk. So I will just share my screen. Okay. So now, okay. So you should see the good screen, right?
Yes, we do.
Perfect. So I'm very pleased today to present you the application of lips in medical implants, which is the result of a 4-year project, the Laser4Surf project. So I will start with a very short introduction of Rescoll to present you our companies, and then we will present you why we were interested to develop a specific laser texturation and very specific surface treatment for medical implants. I will finish by some results, some key results we have obtained during the project, and the perspective of it. So Rescoll, we are a French small company and based in Bordeaux, southwest of France. We are specialized today in polymer science, surface treatments, and bonding assembly for different kind of activity for different sectors. So mainly for aeronautic and aerospatial fields. But since 5 years now, we are focusing our developments toward medical device application, because we have noticed that there is a large need to bring innovations and to bring support towards innovations in such a field, so we can bring our competency to the customers. So finally, our core business is to support the company in their product developments from the very beginning, from the idea up to the production process and through the validations and the qualifications of new technology. So very briefly, our main activities are split in 3 parts. Research and developments, which is the department which worked in the project Laser4Surf. So as I say, we just bring support for the idea and the conceptions and the design and development of a new product by material formulations, process development, bringing expertise needed for customers. And then we can do the characterization and validation, all about surface, mechanical or physical chemical analysis under accredited environments. So it brings safety to our customers that the result obtained can be used later on for commercializations. And finally, we can just assume manufacturing process in some cases, especially for medical implant, for example. We manufacturers for our customers. We are CMO company for that, so we can do metal machining, laser marking, or surface treatments. So in the frame of our activities, we have started to work in the Laser4Surf process project for medical implants. And so this is, as said this morning, a European funded project aims to bring lips to mass productions. So what is the interest? So when we apply the specific kind of treatments in the surface, we can bring new functionalities. And this is a very significant commercial advantages for laser, as it does not bring any chemical modifications or bring any kind of extra coating that need to be approved by regulatory, which is a very big burden for medical implant especially. So why do we need to have a surface treatment for medical implants? Basically, the idea was to improve what we call the osseointegration. So what is osseointegration? This is the capacity of an implant to set in a durable, stable manner in the body and to have good interaction with its surrounding environment. If you look at the pictures here, the first on the left, the implants, it just set at very initial stage, and time after time, there is a kind of creation of new bone formation around the implants. And to ensure that we have a correct recreation of bone in the implant, on the implant, we need to minimize micro movements, and this will allow to avoid any premature failure of the implant. This is what we call primary stabilizations. So how we can improve the primary stabilization of an implant? We can play on the geometrical features or hydrophilicity or topographic features. So there is today's very several methods known and applied to improve the surface topography and the surface state of implants, and then to improve the osseointegrations. Mainly, we can just six chemical surface modifications, which is acid etching, anodizations, or chemical coating. So the idea is just to dip the implant inside very acidic solutions that will just abrade, and that will be removing a very extreme surface and create new groups on the surface to bring on new functionality. The other way is to bring to make physical modification, so sand blasting or grid blasting. So here we just like jetting some sands or some grids on the surface, and we will create some new roughness of on the surface. There is a last one which is not written here. This is coating process. So we can apply the coating on the top of a surface of an implant. However, this means an extra process and an extra material, so it's I just put it aside. So what are the limits of commercial treatment today? So first of all, there is no possibility to create features and provide all the structures to guide cell proliferation in specific direction, in preferred directions. And we cannot target specific area because most of the time, not be all implants need to bring on osteointegrity, but just only some part of the implant need to be covered by bones. So we need to have a masking step. So does this mean that will increase the cost of production finally? And the last one, but not the least, this is that this process bring on chemical or dust residue that need to be cleaned. So we need an extra process, an extra step to clean the process, and an extra validation to make sure there's nothing left after this treatment. So in that aim, we were thinking that bring on laser texturations, laser surface treatments could be of great alternative, as it does not induce any chemicals or do not produce any dust or particle during the surface treatment process. So this is where it comes to the idea of Laser4Surf and the interest for us to develop a new laser surface treatments. So the challenge we thought that were very important for Laser4Surf as new surface treatment that could be used for medical implants is, of course, first of all, to improve the osteointegration with predefined topographic features. We should show that they have good mechanical properties, especially after few months of implantations, bring on the bone to implant contact. We should show very good biocompatibility, and finally, it should not release any adverse components. In terms of process itself, to bring it to mass production, and to facilitate its market penetration, we can see that as advantages. It should be clean and environment friendly process, a bit fast and cost effective. Should be applicable on small and complex shapes. So that would mean that we can apply it for very large number of applications. And finally, it should meet the regulatory standards. So that means no metal modifications, no geometrical feature change. And this will help in claiming equivalency, and then just to help a regulatory body to accept these new surface treatments. So how we can just, in terms of topography, improve the quality of the integrations. So we can play on topographic features. So first of all, macro topographic, which is dependent of the design itself of the implants. We can play on the micro topographic features. So we can see here, we will just adapt very specifically the features to improve the cell coverage on the top of the implant. And finally, we have nanotopographic features, to interact directly with osteoblastic cells and to improve the affinity of cells to the surface of the implants. So finally, the objective of the project is to create dual topographic features to play on both improving cells and recognition factors on the cells on the surface to allow the cell to settle on smooth features, but also to adhere on the surface through biological mechanisms. So in the framework of the Laser4Surf project, we were studying various process parameters of the surface. We evaluated the morphological change, the topographic features, as well as cell affinities. We've decided to use titanium-based implants because it's one of the most widely known metals used for medical implants, which is very biocompatible, but it's also quite inert toward cell osteointegrations. So let's say it's a negative control in the sense that it does not bring any functionality on the surface just by itself. So we can just see how the surface treatments give improvements to cell and to topographic features. So briefly, I wanted to show you key results we obtained during the frame of the project. So first of all, we can see here that we have a very good quality of the surface. This is a 3D mapping on the implant surface. So we have a very well organized and very repeatable periods of the surface. And what is very interesting is we can see that according to the process parameters, we can play on the size of the features, but also on the depth of the features. So depending on the applications, we can just very finely tune the surface roughness and the surface isotropy according to the need and according to what we are expecting from the implants. So this opens a large panel of application. So if we look at the morphology, so we see here nanotopography. So we can see very clear and nice lips formed on the titanium surface. And to come with what I've just said, that we can really play on the surface roughness. So this is the raw titanium with a roughness factors of 0.1, and we can just jump up to 0.4 thanks to the laser surface treatment. So we have a very good control of the roughness, and we can just play on it according to what we need, and we can improve the surface state thanks to Laser4Surf. So, and we wanted to compare it with biological property, which is a key features for osteointegrations. So we have done several tests like initial adhesion of cells, proliferations, and finally we wanted to make sure that we have functionalizations, meaning mineralization of cells on the top of the surface. So we can see here very briefly the result. So once again, this is the titanium, and the three last are the laser textures. So we can see we have a great improvement of the mineralization on the surface, and it's even better than a sandblasting surface treatment, which is the 32 and the 33 here. We can see we can improve compared to conventional treatments the functionalization of the surface. The cells are able to very nicely spread on the surface, as we can see here on these pictures. And we can even see the formation of calcium crystals on the surface, which is a clear sign of calcifications on the surface, and this will improve the bone to implant contact. And finally, a few words. So a very interesting finding we had in the project is that we were, as I said, we said this morning, we can treat it very locally, but we can treat also very complex shape. So we can see here, this is a spinal screw. So we can play on, treat it only very specific area with a nice laser pulse macro topography. And this is not a very good magnification, but we have clearly lips on each of the thread, so which is very good for implants. And we have also concluded on the fact there is no adverse component which were released according to biocompatibility standards, and we have an equivalence in terms of mechanical performance. That means that we are with a medical device with equivalent properties, but with improved cell affinities, so which is like a very great advantage. So I will just conclude my presentations. So to say that we have a controlled and homogeneous surface with periodic features. So it looks, laser texturation is a very promising method to fine-tune the surface parameters according to the specifications, to treat complex surface such as plate or screw, and finally there is no modification of the surface. So finally we can say that the balance cost benefits can clearly be achieved thanks to this technology. And a final word that we have noticed that we can create also hydrophobic surface. So one more application, would it not be that lips features can bring on antimicrobial features for medical implants? So that would be the frame of a new project, but this opened a newer application and new interest for the project. So I would just like to thank all the partners which were involved, and thanks to whom we have such a nice result, especially Lasea and Ceit, which were the one who treated the surface and characterized with us all the specimen and all the implants. So I would like to thank you for your attention. Do you have any question? There is no question.
May I have a question as a chairman? So just a general question on how many, for example, in these screws that you had how many of them must be treated per minute or per second in order to, do you reckon, in order to be cost effective, this method of what's the target of fabrication in terms of quantity you want it to be?
Yeah, this is yeah, especially for screw, which is it's quite difficult to treat screw today with conventional methods, because it's a very very complex shapes. But let's say that for sandblasting, the interest is that we can treat all in the same times screw, whereas with surface treatments we have to treat one by one. So let's say we have a few seconds by screw treatment, which is clearly achieved here. It's a bit longer process, but I think it's valuable compared to the benefits we can claim thanks to this technology.
Mm-hmm. Okay, thank you, Marilys. Any other questions for this particular application? Okay, so if you have any question, just write it down in the chat or in the questions and answers, or you can just do it at the end and make them at the end orally. All right. Thank you, Marilys. That was brilliant. That was so good. Okay, so moving on, we have a second. We have a second speaker, José Luis de la Peña, from Fagor Automation, which is going to discuss the application of lips in optical encoders. So, José Luis, whenever you're ready, please proceed.
Hello, everybody. Can you see my screen?
Yeah, yeah. Everything is all right.
But not in the. Hi. Okay. Good morning, everybody. My name is José Luis de la Peña from Fagor Automation, and the title of my speak is Application of Lips in Optical Encoders. We are 3 people involved in this project from Fagor. And well, first let me present very briefly our company. Okay, Fagor Automation is a Spanish company located in Spain, and we develop, manufacture, and sell all the devices related with the automation systems in machines, mainly in the tool machine environment. We manufacture CNC, numerical controls, axis motors, power supplies and drivers, as well as encoders, optical encoders, enclosed, open, linear and rotary, even incremental or absolute. And we are located worldwide, okay, with different offices and headquarters. If you don't hesitate to visit Fagor Automation for more details, okay? So, well, let me show you very briefly what is the application. When we have a machine and you want to mechanize a piece, okay? So you have a program to do that, and the program is run in the CNC, which send the orders to the motors or to the drives in order to locate the tool in a certain position. Okay, but for doing that, in somehow the tool, close to the tool, a device to control the position at every time is required, just to give that information to the CNC, this information back, in order to close the loop and to give the following order. So this is basically what an encoder is. It's a device to detect and measure relative displacement between 2 elements. And now we are going to talk about linear optical encoders, not rotary, okay? So here you have a scheme about how an encoder looks like. We have 2 parts. One part is fixed and the other part is mobile. The part fixed is called tape, and the mobile part we are calling reading head, okay? So basically the way it works is by the interaction between 2 diffraction gratings. We have a diffraction grating engraved on the tape and a diffraction grating in the reading head. And from these interactions, okay, right here you have the scheme. From this interaction, we obtain in a certain part of the space an image that is modulated accordingly to the relative displacement between these 2 diffractions grating, okay? And this image is projected over a detector, and the detector converts the image, the optical image, into electrical signals that are sent to the CNC. And this is the way that we measure distances and we measure the presence of movement, okay? I would like you to have a look to these pictures, okay? Because this is an analogy between the camera of photos and our device, okay? It's quite similar, okay? We know that a lens is a device by which an image of an object is projected somewhere in the space. In the same way, by means of our mask, okay, we are able to project an image of our tape somewhere in the space, okay? And as we know, as the distance between the object and the lenses changes, the position of the images always changes. But here is the same. As the distance between the tape and the mask changes, the position of the image changes, okay? The point is that the photo detector, the detector is placed in a fixed position. So as or here the screen. So as the distance of the object and the lens, or the tape and the grading varies, the image varies, and the projection over the detector or over the screen are better focused or not. Okay. So basically we say that the quality of the image depends on the distance between the tape and the mask. And the quality of the signals provided by the encoder depends on the quality of the images, okay? As big as, okay. And why this is important for us? Because we have a kind of encoder called the contactless encoders, okay? Where the end users, he gets the tape by one hand and the optical, the reading head by the other hand, I mean separately. And he's the responsible of the mounting, okay, the device. So the point is that we send manual instructions saying that this device works correctly when the distance between the reading head and the tape is a certain distance, a certain gap, theta 0, okay, plus minus a certain tolerances, okay? Because here I can repeat, no? Here we have the tape, we have the light illuminating the tape, the mask, and the detector. Okay, this is the optimum position where the image is well focused and we have a good signal. Okay, and this good signal is sent to the CNC. Okay, with this position. But as the distance between the reading head and the tape changes, okay, the images start to be worse. So the information that the reading head can send to the CNC could be less accurate or less precise. Okay. So in this way, the customer is the responsible of the mounting, of the responsible of the well working of the device. So we are giving him a tolerances of delta, but what we are dreaming about is about having a tolerances of infinite in order to get an easier mounting process. And in this way is where the project Laser4Surf can help us. Why? Because we have realized that the laser texturization, by means of the laser texturization in the processes, we obtain the famous lips which we are talking about, okay? And right here you can see the lips. But I am comparing here our current tape, okay? And the tapes manufactured by with this technology. And we observe that the presence of lips, we have realized that the presence of lips has provides to the diffraction gratings, okay, engraved over the tapes, a new polarization properties that we have explored. I mean, in addition to the optical diffractive properties of the tapes, by means of the presence of these extra lips, okay, an extra new polarization properties has came up, and we have explored that. How? Well, we have developed a new optical reading head containing polarization components to interact with the polarization new properties of these tapes, okay? And what we have done is just to get the different images, okay, when we vary the gap between the reading head and the tape. Okay? By doing, and with these images, we obtain the signal sent to the CNC. Okay, and by doing this, we obtain what we call the encoder installation tolerances graphic. Okay, so this is the comparison. The black line show you the encoder installation curves in our current product without any polarization components. Okay, while the blue curve is showing the new the graph that we have obtained when the polarizations is included, okay, by means of the lips, by the presence of the lips. So here you can see that the arrows show the mounting tolerances, okay? So we can observe that the tolerances have been increased, very importantly, due to the presence of lips. So this is basically the summary, The Laser4Surf, with Laser4Surf, we have the laser texturization tooling, okay, that provides the presence of lips. And the presence of lips gives to the tape a new polarization properties that can be explored. And by using a new optical reading head containing polarization components, we are able to get new graphics, new encoder installations tolerances, softer, I mean, with higher tolerances. And this increasement of the tolerances are could be given directly to the end user, okay, in order to make it easier the installation mounting, okay. So basically, we had to finish with one sentence. We would say that the presence of lips open new doors for the development of more robust optical encoders for us, for Fagor. So thank you very much for your attention. If you have any questions, I am ready to answer, I guess.
Thank you, José Luis. I think that was great. Probably that was an unexpected and not an unexpected result. The thing that you had this polarization response from the lips, or was something that was actually expected from at the beginning.
Well, the presence of lips, I mean, the nanostructures are by themselves a polarizer.
Right.
Okay, one way you optically, one way you have to create a polarizer is by doing a very, very low period grading. Okay, right. So once we observe the presence of lips, okay, we subject that maybe a polarization behavior could came up from this texturization.
Right.
Okay.
Okay. We have a couple of questions coming up for you from Marcelo Bianchi. Is the pitch of conventional and lips line the same?
No. No, well, the period here is 20 microns, okay? The nanostructure, the leaves are, the period of the leaves is about nanometers, okay?
Right.
And right here, you can have the concerning the duty, you can have 1010 or 713 or 614. This is just an example, okay?
Right.
But the pitch is always 20 microns in our encoders. But it's true that smaller is the period engraved on the pitch, engraved on the tape. More accurate will be more accurate will be your position. Okay, and with more resolution, the encoder can give the information to the CNC.
Okay. So the pitch it's not the same in this case, or is it the same?
Not in this case, but this is just an example. Okay,
yeah.
But
okay.
But we have dealt with other samples. Well, actually, we have received about more than 20 samples, either from Lasea and from Ceit. Thank you for that.
Right. You're welcome.
Yeah, and the duty we have dealt with different duties,
right.
And it's important showing that on all of them we have observed the same behavior. Okay, this is just an average or just an example of the behavior found, but it's very important to remark that we have found the same behavior in all the samples that we have explored. I mean, in more than 20 samples, okay? And the presence of this double lobe okay, has came up in all the samples tested.
All right.
Okay, with different pitches. Okay.
Yeah, that's brilliant. Another question from Liliana Cangueiro. Can you increase further the resolution of the encoder with LIPS texture tapes? Can you increase further the resolution?
Not the resolution. I mean, the resolution is related on the period of the engraving.
Right.
Okay. The smaller is the period, more accurate and more resolution you can have. But I think it's not straightforward related with this. Okay. Then the presence of leads, from our point of view, it's more related with these new polarization properties.
Right. More to the robustness more than the resolution.
Yeah.
Yeah. Okay. So I think that was all. Thank you, Jose Luis. Thank you, everyone, for.
Thank you very much, and thank you to all of you for supporting during all the project, and for sending out all the samples that we have required for you. Okay.
Okay.
Thank you very much.
Let's move on. Yeah, let's move on for the third success story. Third application. It's going to be Dr. Elena Gonzalo from CICe-CEGASA and CEGASA. Is the application of leads for batteries, for electric batteries, which is a very different topic of this other two. Elena, whenever you're ready.
Thank you, Yago, for your kind introduction. I hope you can see.
Elena, I can hear you, but very low volume.
Okay, so I'll try to keep closer to the microphone.
That's better. Yeah,
okay, thank you, Yago. I was saying that thank you for your kind introduction, and it is a pleasure for me to participate in this final event and to be able to show you all the results we got by using the LIPS surfaces that Ceit and Lasea provided to us. So the title of my talk is Functionalized Copper Current Collector by LIPS to enhance the performance of lithium-ion battery. My name is Elena Gonzalo. I am a researcher at CICe-CEGASA, that it is located in the north part of Spain, in the Basque Country. And we are devoted to study the electrochemical energy storage and thermal energy storage. In order to get you all into context, as I know that most of you will be from different fields, I would like to double check with you what an automotive battery pack is. So here you have in the screen the picture of a battery pack that is composed by different modules, and those modules are formed by different pouch cells. What is a pouch cell? Here you have a scheme of a multi-layer pouch cell that is formed by the cathode, that is the one of the electroactive material that is cast or deposited on aluminum current collector, and the other part is the anode, that is the other electroactive material taking part in this game, that is deposited in copper collector. Between the anode and the cathode, there must be a separator where the electrolyte is placed, and in order to not to have any short circuit in the cell. Getting closer to a monolayer cell, you can find the anode, the cathode, and in between the separator and the electrolyte. And what is going on inside the cell? The ions are moving from one place to the other place of the cell. In this particular case, we are looking at the discharge part of the cell, and the electrons are going out from this cell in order to move, for instance, this car. So which was the goal of our part in the project? As end users, we had to test these surface modified current collectors, the copper current collector, in order to be able to increase the number of ions moving from one side to the other part of the cell. And at the end of the day, what we wanted to have was more energy to move this car. So getting closer to what a cell is, and this is mostly what you have in your mobile phones. You will have the anode, the cathodes, the current collectors that I told you before. For the anode, it will be the copper current collector, and for the cathode, it will be the aluminum current collector. In this particular case, we have graphite as anode material and lithium cobalt oxide as cathode material. And in between of those, we have the electrolyte. This is a scheme of what is inside a cell, and you can see here what LIPS have done in our current collectors. We have, or our partners have done the structure modification in order to get some different characteristics of our cells. So these two particular partners that have already spoken, Ceit and Lasea, have fabricated the LIPS current collectors that you will see today in my presentation. I will be only focused on the anode material, although as David was saying, they have done an excellent work also in aluminum current collectors, but the main part of my talk will be only copper current collectors. So the aim of this nanostructuration was, on one hand, to increase the mass loading of the electrode materials, and on the other hand, to improve the addition between the electrode material and the current collector. If we do that, we will be able to have higher cycle life of the battery and better electrochemical performance when we are playing at high C rates. I will explain it to you a little bit later. We have tested these current collectors in two different devices, not only in coin cells, but also in pouch cells. That was the objective, the goal of the project. Try these current collectors in a monolayer pouch cell as our demonstrator. As you can see from the left-hand side to the right-hand side of the slide, firstly, Ceit was fabricated coin cell shapes of the nanostructured areas in the 50 microns copper current collectors. We were testing all the different parameters they were playing with, and finally we got the best ones for our electrochemical response. Those parameters were transferred by Ceit to pouch cell size with thinner copper current collectors, and at the end of the project it was scaled up by Lasea, keeping all the same parameters that were useful for us in this A4 size shape for multiple pouch cell electrodes. As some of you are not familiar with the steps we have to follow to prepare these electrodes and the role that the current collector plays in these steps, I will briefly summarize which are those steps. So the first part is get an homogeneous slurry, an homogeneous mixture of the active material that in our case was an oxide of lithium and titanium, the LTO, and the conductive additive plus a binder to attach the three components to the in-between and also to the current collector. In order to do that, we need to use a magnetic stirrer, as you can see in the pictures, and we got this final result that it is an homogeneous ink with a particular density. The next step was to cast this ink on the copper current collector. Here you have all the series of pictures of this A4 size current collector nanostructured by Lasea that was done with the help of a blade in a vacuum table. And we were able to control the wet thickness of the electrode. So this is our final result, the anode electrode. And what we had to do after that was cut the electrodes, press them and dry them to be assembled in a cell. Which were the two configurations we were playing with? One was the coin cell configuration. We had to cut the anode in round shape for to be assembled in coin cells. And we were testing half cells versus lithium metal or full cells versus the positive electrode. The second device we were assembling was a pouch cell. We were following more or less the same steps. We were cutting the electrodes, we were selecting the cathode material, and we had to determine the correct mass balance, that is the correct mass ratio between the positive and the negative electrode in order for the cell to work properly. We were assembling the cell and using the separator in order not to have the short circuit, assembling, doing the pre-cycle, degassing the cell, and finally we got this pouch cell. where to do this or to assemble these devices. If we were speaking about coin cells, we normally assemble them in these argon filled glove boxes where we have a very small amount of water and oxygen, less than 0.1 ppm. But if we are playing with pouch cells, we have to go to our dry room at CICe-Energy Gune to assemble them. Here you have a summary of all the characteristics of our dry room. Previously, to get the electrochemical response of our cells, we have to do the electrode characterization. Of course, I'm not going to go into detail of all the characterizations that we have made, but I will just check or focus only on two different characterizations. One of those is the morphological characterization that was carried out by scanning electron microscopy. We wanted to check the homogeneity of the sample, but also we wanted to study the cross-section of our electrode. To do that and to get a perfect cut of the electrodes, we had to use the ion milling technique. So in this slide, you will see some examples. On the left-hand side, you have a picture that you already saw in previous presentations of the lips and the direction of the casting that we were using. And the rest of the micrographs are the pictures of the cross sections. Going from the A to the D, we get more magnification of our electrode. And you can distinguish from the copper lips current collector and what is on the top, that is the LTO electrode. If you check carefully the ratio or the border between the LTO and copper lips, you will see that it is perfectly cast and perfectly aligned. So the addition between the LTO and the copper lips is quite good. One more test that we did was the peeling test, because we wanted to check and we wanted to compare the addition that we got with our copper lips current collector and with the bare copper foil that we have in the lab, the one that we normally use. To do that, we use this testing machine, this Instron single column universal testing machine. And here you can see some picture of two electrodes of that were cast on bare copper foil and two electrodes on copper lips current collector. And just by eye, you can distinguish that after the peeling test, in those electrodes that were cast on bare copper foil, there are more parts of the electrode that have been detached, so more active material that has been removed. While in the other two cases, with the copper lips, most of them are, most of the surface is covered after the peeling test with electrode material. So we can say that the as prepared copper lips electrode show better adhesion compared to the copper bare electrode. And in order to have a look on how this test has been done, let me show you a very short video, like a 1 minute or less than 1 minute video of how this peeling test is done. We can check by eye which is the addition, but also we can monitor and we can control the strength that we need to apply to remove the electrode material. And finally, we will get a number of this strength. So when we have our electrode already characterized, and we are able to check the electrochemical response of our pouch cell. So here you have the pouch cell. We check the operation voltage before cycling it, and then we put it in the holders to be tested in our battery testers at CICe-Energy Gune. So here you have the electrochemical response of our cells, the comparison between the bare copper foil electrodes and the copper lips. I will show you only these two tests. Of course, we have done several tests in many different cells. On the left-hand side, we have examined the cycle life of our batteries. And we check them at 100 cycles at a current of 1C. What does 1C means? We were applying a current to charge the material in 1 hour and to discharge it in 1 hour. And after 100 cycles, we saw that there was better capacity retention of the copper lips, the purple one graph, than in the bare copper foil, the bare copper electrodes. So it means that we got better cycle life of our pouch cells with copper lips. current collectors. In the case of the right-hand side graph, where we did the C-rate capability, what I mean is we were increasing the current density from 0.1 C, that means 10 hours to charge the material and 10 hours to discharge the material, to a faster test, I mean, applying current to charge and discharge for 30 minutes, you can see clearly the difference between the cells that were cast on copper lips, these pink ones, and the ones with bare copper foil. There was a huge decrease in capacity when we were going to very high current density. So we got better electrochemical performance at high C rates for the copper lips. After the electrochemical testing, we wanted to do a postmortem study on the cycle cells. And here you have the series of pictures of how we open the pouch cells. We cut them, we disassemble them, and we separate the cathode and the anode. Here you have the anode. We have to rinse it in the solvent, and then we are able to do all the characterization techniques that we have in-house. Again, I am only going to focus in two, in the scanning electron microscopy. Here you can see the images of the cross-section of the electrode that was cycled, and even if it was cycled and it was suffering a stress of charge and discharge or applying a current, the addition was perfectly fine after cycling compared to the pristine electrode. And when we were doing the peeling test, after cycling these copper lips electrodes, although there was a lower addition than the pristine electrodes, it was much higher than the cycled pouch cells with copper bare electrodes. So in order to conclude, I would like to say that the nanostructuration results in an improved C-rate capability for all electrodes and cell configurations. Batteries can be charged and discharged faster while keeping the same or higher current densities. Our prototype, our full pouch cell, demonstrated higher capacity retention, and the cycle life was improved. I hope that we have been able to demonstrate the beneficial effect that the nanostructuration on current collector has on the battery performance of our batteries, the ones that we have tested. So in order to conclude, I would like to thank the financial support from the European Union, all the partners that have actively contributed to this work, and the rest of the partners of the consortium, and of course all of you for your kind attention. Thank you. And if you have any question, I will be more than happy to answer.
Thank you, Elena. That was brilliant.
Thank you, Yago.
See if there's any questions. If they pop up any questions. However, we are running a bit late, actually. So we may just go to the next talk, and if there's any questions raising up, there's one coming up. Slide 11 from Marwan is asking in slide 11, can you explain the crossing in the curves of slide 11?
Just a second, let me go back to slide 11. The crossing in the curves here in the left graph, do you mean?
Yes, I think he refers to that one.
Yeah, actually, the one as the cycling test was very fast, there are a small fluctuation of the data due to the temperature conditions of the room. So at the very beginning, the bare copper foil was performing better. It was giving more capacity electrochemical response, but at the end of the test, the stability was improved when we were using the copper lips. These small undulations could be due to the temperature, but in both cases, they were tested at the same conditions.
Okay, there's another question from Marcelo Bianchi. What is the structure geometry on CU-CC, copper CC? What is the structure geometry?
What do you mean with the structure geometry?
What does it mean?
the thing is that we were, I mean, all the details from LIPS I cannot disclose, but the geometry that we use for coin cell was the CR2032, the ones that we were using, and for the pouch cells, it was around 10 centimeter per 10 centimeter square.
Okay, that's apparently what he was asking for.
Okay, thank you.
Thank you, Marcelo. Thank you, Marwan. Thank you, Elena. Let's move on for the next and last talk. It's going to be from the speaker Mikel Gómez-Aranzadi from Ceit, a colleague of mine, with the title New Opportunities for LIPS Technology. It's going to describe other applications of LIPS. So whenever you're ready.
Yes, thank you. Please, I need to share that. Oh, okay, thank you. Okay, so
Mikel, could you just take the microphone a little bit off your mouth because we can hear every breath, just a little bit.
Sorry, now can you hear me?
Yeah, it's better now.
Okay,
Thank
sorry.
you.
So I'm going to speak about some applications apart from the ones that we have developed during the project and to see what are the opportunities that LIPS offer, especially after this project in which we were able to construct an industrial system to fabricate the LIPS in a more serial and industrial way. Okay, so this is the overview. I'm going to give a big introduction about the three applications that we did in this project, and then I want to speak about the different applications. I'm trying to be fast and to the point because we are a bit out of time. Okay. So as you know, these are the three applications that we have developed during the project. Okay, we did an announcement of implant integration in which we were searching the hydrophilic properties in the material, in this case in titanium. But we will see now in some applications that if we go hydrophobic instead of hydrophilic, we can have another applications that could be interesting too. We also improved the tolerance of the installation of encoders and the signal by including LIPS in the gratings, and we also increased the efficiency of the battery by texturing the collector, and also a life cycle of the batteries was improved. Okay, so taking this into account, I'm going to start with the Lotus or Lotus effect. The Lotus is a plant that is, as you know, very important in the Eastern Asian cultures, because although it normally occurs in mud and in dirty environments, it's always pristine. And this is thanks to the structure that both its leaf and its flower have, that is what we would call hierarchical structures, microstructures covered by nanostructures. So what the LIPS can let us do is to replicate this type of applications, or this type of structures in industrial applications. One will be like to avoid the de-icing of the planes, as in we had a brief preview in the first presentation. So you see here on the right a video in which some drops are dropped in a non-patterned surface, this is metal, stainless steel, and then when we drop the water on the squares that are patterned, we obtain an hydrophobic response. So we can translate this to the wings of the planes, as some groups are trying to do. We could avoid the water to attach to the planes, that water, because that water then will convert to ice, and we can avoid this. We can avoid the de-icing and save both time and money. Okay, so this is one of the applications that could be done using LIPS above other or alongside other microstructures. In the case of amphiphobic surfaces, these surfaces are in which we want to do is to avoid both the attaching not only only water but other elements like fat, for example. In extracorporeal membrane oxygenators, these are systems that work as a support and work like as an external lung and heart. So in this case, we want to oxygenate the blood and to take out the carbon dioxide and to inject oxygen. This is done through membranes. The thing is that in the blood, apart from red blood cells that we can see here, there are other elements, and in this membrane, they can be stuck and clogs can be produced. So one application for this will be to texture these membranes to make them amphiphobic and to be able to avoid the cloggings, for example. Okay. Another type of surfaces that I think Rescoll has hinted in the end of their presentation will be antibacterial surfaces. This would be, instead of making the surfaces hydrophilic, to make them hydrophobic. And for example, these are bacteria, and the thing is that when the bacteria is attached and they reach a certain number, they try to form a biofilm that is very difficult to remove afterwards. So in this work, what they done was to create lips in a certain orientation and structure, and you can see there that with a non-treated surface, that are the matches A and B, the biofilm is totally formed, so it will be very difficult to remove the bacteria. But in the C and D, with the lips, the biofilm is much more sparse and it could be more easily removed. So this was a work, a researching work, but with the new system of Laser4Surf, this could be done in an industrial way, for example. Okay. So in the case of lamps, we can also texture the element that creates the illumination. For example, in the case of gallium nitride-based LEDs, it has been researched, and you could improve the illumination by a 30% just texturing the surface of the LED. And also, in the case of incandescent light bulbs, if we structure the filament of the bulb, we can increase the illumination by for the same amount of current that goes through the filament. Okay. In the case of solar cells, for example, lately we have these flexible solar cells that are based in thin film silicon. They are more flexible, more easily to install in surfaces that are not totally flat, but the yield is lower. So what we could do is to structure with lips the surface of the different elements to try to trap more light and to keep it there to increase the yield. This work was not done with lips, was done with other type of technology, but again with the system created in Laser4Surf, this could be made in an industrial way for this type of solar cells. Okay. This is an application that we have researched in our group by the Dr. Martinez Calderon, that is at the moment in the Auckland University. So at the moment, more and more, the market is researching, or the research area is very strong in photonic chips, because something that they are going to replace the electronic chips. So in this case, the thing that you see in the left hand side is an optical fiber, and we need something to couple the signal to the photonic chip. In this case, it has been done in silicon and with a surface grating in order to couple it. But we have researched is that if we use, for example, diamond, tuning the depth, the width, and the period of the lips, we can choose, as to say, what waveguide do we want to couple. So this could be used as a filter, and depending on which part of the signal do we want, we could tune it depending on the characteristics of the lips. Okay. So to end, we know from nature, as you can see here, these two butterflies, that it is possible to generate colors without pigment. in the case of butterfly wings, as we said. There are even some butterflies that have transparent wings, okay? So knowing this, we can use the lips to generate aesthetic effects. In this case, we can see a surface of stainless steel that when looking at it perpendicularly, we don't see any difference, okay? But for example, as lips are orientated differently in the lower hand side and so in the lower part and the upper part, if we turn it in the X direction, we only see a distance in the upper part, okay? In the upper half. But if we turn it in the Y axis, we only see a high distance in the lower part. So what this does tell us is that tuning the period and orientation and the depth of the lips, we can obtain one specific effect depending on the point of view of the viewer. So, and also there are some research which consists in changing the period of the lips continuously in order to obtain the same color from a specific point of view. This could help in making sure that the viewer is seeing something and the rest are seeing other thing that is tailored for the angle of view. So this could be another application that can be done with the fabrication and mass production of lips, okay? And to end, there is the texturing of injection molds. The good thing of, or the important thing of using injection molds is that once you have textured one insert, you can mass produce parts, injecting with them into polymers, okay? Normally, this injection molding technology is very well suited for macro and micro structures. But for example, if we have a fluid enough polymer, we are able to reproduce the lips. As you see here, the iridescent effect, that's in an injected part, not in an insert. And in the right-hand side, the big vertical lines are separated more or less 10 microns, but the small ones that are horizontal are lips. So if we are able to use a specific polymer that suits the reproduction of the lips, we can translate the applications that I have just showed in a industrial way by reproducing it through injection molding. So that is all from my side. Thank you very much. And if you have any questions, please let me know.
Thank you, Mikel. I think there are a couple of questions there from Massimo Bonfante about lips for antibacterial. Which is the typical processing times? It's always an issue, processing times per unit area, for example, per centimeter square.
Well, that's not the specific of the application. That's specific of how much area we can cover with the scanner. So with industrial process that we have developed, I don't know, depends on the beam spot. I have to say that I didn't say that this has to be very fine-tuned. So the important thing, the time-consuming thing, is to tune it very well, because it has been shown in research that if you generate the lips in a different way, instead of hampering the adhesion of the bacteria, you enhance it. So the most important thing is to define very well the process. Once the process is defined with the new system we have, we should be able to cover, I don't know, maybe I don't know, people from Lasea could answer how fast can we go by producing the lips. So,
but surely we can put some number there. Maybe someone from Lasea can help you out. Which is the typical processing times per unit area for antibacterial?
for lips in general.
With lips, I don't know. It can be, if we can do. Anyone can give a number here from the consortium.
So this is David from Lasea.
David?
Yeah, so I've got some numbers, but there are more for 3 targeted applications so far. So for the batteries and also for encoders. I don't know if I can give those numbers publicly, but we we haven't done any processing for antibacteria unless on no, we haven't done antibacteria on large surface and flat surface.
All right. Okay. Marwan is asking about slide 10. What about the losses in this case, in the case that you exposed, Mikel, in slide 10, which is, of course, the coupling in the photonic chip. The lips are not as regular as grating couplers. Fabricated with a standard lithography and etching process. Of course, they are not. What do you think about the losses?
Well, this was one work that we did. We published in scientific reports about using the diamond, and the results we obtained were quite good. Of course, as this has not been addressed in an industrial or a big area point of view, maybe for the moment that could be the case. Of course, there are other technologies that are more regular, as you see there in standard lithography, but in this case, the thing is the interest is to research to see if we can overcome that. Okay, so that would be a thing. I will take a look to the Trace Clean project, as you say, to see what you have done there. Okay, thank you.
Yeah, I agree with Marwan that of course the standard lithography would have better coupling properties. However, the nice regular lips we had in the last stages of the project, we probably have to do a good job about this. It could be very interesting to benchmark one against the other, not only in terms of effectiveness, but also in terms of time, cost effective. There's another. Well, there's another remark from Marwan saying that wow, that's a lot. 12.5 centimeters square per second was achieved in interacting surfaces.
Okay.
And Marcello Bianchi said that what led to choose femto versus picosecond laser? Why we chose a femtosecond laser for this project, not the picosecond laser? That's a good question. From our expertise, maybe some people in the consortium would like to say something as well. But I can start by saying that from our expertise in process production, I think that femtosecond lasers give more. The shorter the pulse, the better you have the resolutions in the lips, the better remark they are, and these kind of things. Of course, you can have lips with nanoseconds and with picoseconds. Picoseconds are mostly okay, but you want to have a better control on not only the process but also in the shape. I think we have to consider having the less temperature in the surface, and the shorter the pulse, the less temperature on the surface. You can argue that this can be done with pulses less than 10 picoseconds for most of materials, but we wanted to play safe and go with femtosecond, be sure that we don't have this temperature. Any other inputs for this femto versus picosecond laser for lips? Anyone? No, I'm alone in this. Okay, so I hope we answer all the questions. That were very nice questions and very useful remarks. Thank you very much. Let me just I think this is the end, but first, before the end, I'd like to give a word because Elma, which is our manager for dissemination, maybe wants to say something else about the availability of the information of this conference, Alma?
Yes, well, thank you very much. Just very briefly, I just put in the chat some of our links and where you can follow up on what else is happening in the last days and perhaps even beyond that. For the Laser4Surf project, we have obviously we have the website where you can basically find a lot of more information. We also have a Twitter and LinkedIn account where I think a lot of you are already active, and you can follow us and see if there are news coming in. And we also have a ResearchGate account, so there you can also follow up in case there will be upcoming or already existing scientific papers on what you've heard today. And yes, there will be also, just very briefly, there will be a video that we have created that will be published probably tomorrow on the Laser4Surf project, just to get another overview on it. And this conference will also be, we need to adapt a little bit, but that will also be made public in the coming days, I would imagine. That's it from my side.
Okay, so that's 10 minutes more than we actually anticipated. I'd like to thank you all for joining us here in this final conference of the Laser4Surf project. I think it's been a pretty good speakers. Thank you for the speakers. Thank you all for joining. I don't know. Hope to meet you in the flesh sometime in the future. And if you want any further information, Elma had just pointed out the way to go. Hope you enjoyed the conference as much as I did, and hope to see you soon. Bye-bye. See you. Stay safe.
Thank you.
Thank you. Bye-bye.
Thank you very much.
Bye-bye.
Thank you.
Thank you.
Bye.